to hand over the training of this keynote speech session to Professor Bin Chen, and let's give him a big hand. Thank you.
Thank you, everyone. Good morning, and I'm very happy to chair this section this morning. This section is the concluding speech of our conference. We are pleasure and very honored to invite Dr. Xin Xue from Microsoft Research Asia, China, to give us speeches workings on human behavior data. Dr. Xue was graduated from computer science from University of Science and Technology of China in 2001, and at the same time he joined Microsoft Research Asia and workings on spatial data mining, location-based service, social networks, and ubiquitous computing. He has published over 160 journal papers and conference papers. Also, he has more than 50 patents filed or granted. He is also the active board in so many international journals, such as HM and Springer and SBO. Okay, so today he will give us the talks on the titles as talking about knowledge graph based on human behavior data. So let's welcome Dr. Xue.
Okay. Thanks, Professor Chen, for the introduction. Actually, it's really my honor to be here to introduce my recent research work. And today I will introduce our work on building user knowledge graph based on human behavioral data. So actually, in this talk, I will first introduce my research vision, and then I will introduce 3 of our recent research projects. So first, I will introduce why we are working on this area. So basically, I think the conference is about big data and the social informatics. So basically, I think we have seen in the area of big data, there is a type of big data which is very important. That is the big data generated by the users, by ourselves. So if we look at a day in our life, you will find that a lot of user activities in this physical world have already been recorded. For example, if you set up an alarm clock, maybe on your phone, and actually your phone will know when you will get up. Actually, even you haven't set up this alarm clock, the phone will still know. Why? Because I think for most of us, the first thing you wake up, you will do is you turn on your phone and read your social messages. In China, maybe WeChat. And maybe the last thing you do before you get to sleep is still you check your Facebook, Twitter, or WeChat. So actually your phone will definitely know when you get up and when you get sleep. So it knows the quality of your sleep. In addition to this, you may set schedule either on the internet calendar or on your phone. So this actually service knows your schedule for every day. And if you take taxi, the taxi actually have sensors, have GPS sensors. So the trajectory of the taxis have already been recorded. And even you don't take taxi, you take subway or buses. this subway system, or if you swipe a smart card to enter the subway or get on the bus, this smart card will also record your data. Actually, later I will introduce one of our projects on how we use this data to recover the human mobilities. This figure just shows we use taxi trajectories in Beijing to visualize the hot air regions in Beijing. So this we can easily see some regions in Beijing are more popular than the others. We have done a lot of work based on taxi trajectories. And on social media, for example, if you go visit some other cities, you will write reviews for hotels and restaurants. And these reviews and for hotel and restaurants will indicate where you stay and also indicate your interest. So we have get some data from social checking websites and from those review websites and use those for recommendation purpose. And the next, we will see how we can leverage this knowledge generated by the user data for different kinds of application. There's one important application we call it personal assistant or chatbots. Maybe you have heard of Facebook released app recently. App is a personal assistant on Facebook. It can you can talk to them and ask questions to the personal assistant. Microsoft also have released we call it Cortana. How many of you know what is Cortana? Maybe you can raise your hand. Yeah, it seems no one here knows Cortana, but basically maybe this is not for advertising, but Cortana is Microsoft personal assistant on Windows Phone. So if you want to know, you can buy a Windows Phone. So this is Cortana. We have a lot of collaboration with the Cortana team on how to mine the user data and how to make recommendations and how to infer user interest based on this data. And in China, Microsoft China team also released, we call it Xiaoais or Xiaobing. Xiaobing is a chatbot. Chatbot is a type of personal assistant, but more good at chatting with you, like chit-chat. For personal assistant, that is more serious, but chatbot is more for fun. So for Xiaobing actually is a personal assistant who can talk to you. In China, actually, Xiaobing already has about 20 million users in China. I think almost the population of Taiwan, I think. And also some other companies like Baidu released their personal assistant, Dubi. And Google has Google Now, and Apple has Siri. So a lot of personal assistant chatbots have been released in the recent years. And I heard in the KDD this year, in the banquet talk, Professor Bing Liu, I think he's the chair of CKDD. He mentioned actually Xiaobing in the banquet talk. He also mentioned that personal assistant and chatbots are definitely a future trend for data mining or for big data. And why we want to understand users, how this can help the personal assistant or chatbot. Because I think for personal assistant like Siri, basically you can talk to them, you can ask questions, and you can make some orders. But basically, I think if the personal assistant, if it can understand better about the user, it can do some proactive things. That instead of only talking to the personal assistant can also initiate the discussion with you. So we have some collaboration with Xiaobing in the Microsoft China team. Basically, we have defined some scenarios. Actually, these are all real scenarios. The font size is a bit small, but I can introduce the content here. So basically, if Xiaobing knows you always sleep very late, that means Xiaobing actually from your previous chat history or from other data. If Xiaobing knows you always sleep very late, Xiaobing will care about your health and ask you to sleep earlier. So I think this is a better robot than the traditional personal assistant. Also, if Xiaobing knows you came from some other province like Sichuan or from Taiwan, Xiaobing can talk to you in your dialect. That means Xiaobing can switch his language and talking to you in your style. And from your other history, Xiaobin may know your interest, like if you are interested in some Korean band called EXO, Xiaobin can also talk about EXO with you. So these are all some scenarios that how we can leverage this data. Of course, we have some other scenarios like advertising, like recommendation. All these scenarios need a better understanding of users. So we want to build a user knowledge graph. This user knowledge graph can be leveraged in these scenarios. So we start with data. This data include data from Microsoft or from other companies. Like we have data from Bing, our search engine, or from our Exchange, from Outlook, from other social sites like Skype or Yammer. And also we get data from the public social network like Twitter or Chinese Weibo. And also we want to use data from the public web, for example, in some news or academic websites, we can also find information about users. So first, we want to link all these data together by user linking. Here, user linking, we have worked on this for several years, how to link users according to different information, like from their profile, from their social structure, or from their self-disclosure. After linking these users, we can get data from each user on the different websites. Like we can link the user in our service and the user from some social websites. And after this, we can infer user knowledge, like user profile, user location, user interest. Later, actually, I will introduce how we infer user location and make location recommendation based on the user data here. We have also worked on infer user relationship knowledge and infer the social network knowledge, like the community involvement and the network information knowledge. And then we want to link all this knowledge with the knowledge graph. Knowledge graph, I think, is a popular research area, but here we want to leverage the experience in knowledge graph and link this knowledge to make better inference about the user. In China, we also, in Microsoft, we also have a knowledge graph called Satori. Basically, it's similar to Freebase. Basically, we have a lot of knowledge about the world, and we want to incorporate this knowledge with user knowledge, and then we can make deeper inference. So basically, this is a vision for how we want to build a user knowledge graph. And then later, I will introduce three of our projects. One project called LifeSpec. Basically, which in this project, we want to start with some social network data and link the users, and then we connect different user data together and basically try to infer the interest for a group of users. And later I will introduce another project based on the user data from some, we call it smart card. Smart card basically is the card for bus and the subways, and use that data to infer the user home and the work location. And later we will also introduce a work on location recommendation based on the user location histories. So first I will introduce LifeSpec. LifeSpec is a work we started in 2012. We are continuing building this platform for getting the more user data. So this basically we want to use the data to explore the spectrum of urban lifestyles. We are interested in understand how users live in cities. So we try to get data from those social websites. Here we cross some data from those Chinese social networks, include Douban. Douban is like a review website for books and the movie and the music. And we have data from Jiepang, is a social checking website similar to Foursquare. And also we have data from Weibo. Weibo is similar to Twitter. We have correct data from multiple networks. Here are the four major networks, including Jiepang, Weibo, Douban, and Dianping. And we have crawled about 1.4 million users. This actually is not the total users, because here we help to study how we can link users across different networks. So we only focus on those users who have multiple accounts in these networks. Because if we only focus on Weibo, actually we can get much more data. Like I think we have like 20 million users from Weibo. And we have crawled their data, basically we call them footprints. Footprints include tweets, photos, check-ins, reviews for movies, books, and music, and other events data. And for some users, they also have entered their user profiles. These profiles include their age, gender, and residence, relationship, etc. This basically we only focus on those public available profiles on these social networks. So we can connect this user profile and their footprints and all the different networks together in this project. In total, we have 53 million footprints, and they have 3 million social links. And among these footprints, we have 39 million check-ins. This table just shows the data in different cities in China. Most data are in Shanghai and Beijing and other big cities. Based on this data, we have carried out different research on different problems. One problem is we want to study some basic statistics of this data. For example, we look at the frequency of check-ins in different cities, like Beijing and Guangzhou. These are two typical cities in our dataset. And the x-axis is the day in a year. So if we look at this, we can find that the frequency is always high in weekends, and especially higher in those national holidays, like the holidays these days in China. We have a lot of events. Usually, users will arrange travels and visits during these holidays. And also we look into different hours in a day. So this is different hours in a day. And we still compare data from Beijing and Guangzhou. And we can find that how people sleep in different cities. So from these data sets, if we only look at these two cities, we can find that Beijing people sleep longer than Guangzhou. So this is interesting because we thought Beijing people works harder. So this looks different. But later we compare this with some other data source from a survey by the Chinese Medical Doctor Association. This also indicates that Beijing people sleep earlier. Beijing people actually sleep about 50 minutes earlier than people from Guangzhou. So I think this is only because Guangzhou is hotter. Yeah, it's like Taiwan, I think it's very hot here. So people here can sleep late, and people can go to the night market and eat till very midnight. In Beijing, I think we cannot imagine. I think we don't have any midnight night market in Beijing because it's too cold. You cannot eat outside. So this is interesting. I think there are some interesting research problems we can explore along this direction. Even I see some paper from other research teams, like in the scientific reports. They study how to compare the mood of people in different hours in a day from data from Twitter. So this is also interesting, whether people is more angry in the morning because they get up too early. So this is a lot of interesting problem we can study. And another research we have studied is about traveling. I think we just talked to some professor here about tourism. So here we study what's the difference between local people and non-local people. Here, local people means people live in a city, and non-local people means those visitors or travelers. So we look at data from 3 cities, from Beijing, Shanghai, and Hong Kong. And also we look at these people came from Beijing, Shanghai, and Hong Kong. So we look at their difference. If we look at this table just shows, for example, this map on the diagonals means those local people, the mobility pattern of local people. Like this is Beijing citizens, their travel pattern in Beijing, and this is Shanghai people in Shanghai, this Hong Kong people in Hong Kong. And this means those people came from Shanghai, but they are visiting Beijing. So if we compare these figures, we can see The difference is those local people basically they travel in a broader range in the city. And for those non-local people, those visitors, they only focus on some, for example, some specific location. I think this based on some conference centers, those airports, those tourism locations. So this is nature because for those visitors, they don't have time to explore the city, so they only go to those locations which are popular or those are important. And also we study their difference. So we try to use this difference to help location prediction. So if we know whether a person is local or non-local, we can better predict their future location. So we have actually sent this paper to AXIP. Actually, recently they reported the MIT Technology Review reported this work, and they show great interest in this work. And we want to further study how, because people are always moving, so we can hardly define who is a local people or who is not. Because, for example, for me, I stayed in Beijing for 14 years, but I don't know whether I'm local people or not. Because there are many people who have stayed for 50 or 60 years. And so we have studied, can we define a degree for a person who is how local he is, and use that degree to study the characteristic of a city, how this city welcome people from other cities. So we want to further study this research problem. Okay, let's come back to the system. The LifeSpec system, basically we developed this system by linking the users across different networks. And this linking, in this platform, we only look at those public self-disclosure data. What does it mean? This means the user shows their accounts on other networks by their profile or by their cross-domain posting. So we only use this public information to connect users. But in our other research, we also try to use some, use in social network structure to connect users, or use their profile or their username to connect their accounts. For example, a lot of people use the same username in different networks. If this name is very unique, actually we can easily know this is the same person. Or some users use the same profile image. This is also very indicative. So this just shows how we connect users. And after connecting the users, we can get their profile, their footprint, and their social links. Because we have both the user profile and the user footprints, we can further study, instead of individual person, we can further study a group of users. A group of users means if we look at users from a university or graduate from a university, or look at users from a company, we can look at this group as a whole and study what's the common living pattern for this group. So we use a topic model to do this. So basically, we first collect all the footprint from this group of users, like this is the group of people from Beijing. And then we build a hierarchical topic model to describe this group of people. So the most common footprints or living patterns we show on the root of this tree, this hierarchy. And on the subtree, we show a living pattern for a subgroup of people. So basically, develop this relational hierarchical topic model to summarize the living pattern for this group of people. So this just shows the result for our dataset. For example, we can compare people working in finance and working in software. So if we compare these two groups of people, we can find that typically, I think for people working in finance, they will read economic books. I think this is very nature because this is their work. And for people working in software industry, they will read computer books and programming books. And I think these are very nature findings. So we can just compare this by comparing these two trees. And also we can compare people in different age. Like we compare people, we call it both, we call them post-90s and the post-80s. Post-90s means people are born in 1990s, and post-80s means people are born in 1980s. So we found that for post-80s, many of them like hot pot, but for post-90s, they are not. They like coffee in the bars. Actually, we have some other comparisons. For example, we compare people from different universities and different companies. There are some interesting results. We published this work in an ACM conference on online social networks, called COSEN. So if you want to find more detail, you can read that paper. So basically, in this work, we have defined a framework for exploring urban lifestyles, and basically the platform called LifeSpec is used to collect the data set and connect users across different networks. And we define a relational hierarchical model for summarizing their lifestyles. So basically, we use this as data platform for further research, for future research. So next, I will introduce another work. Basically, this is, we try to look at the user data and use this data to study human mobility. So this data came from smart card transaction. So smart card means this card we use to swipe to enter the bus and the subways. So we start this work. This actually is a work part in ICTM. And basically, we start this work by a motivation is we always see some gap between the data generated by the source application and the data needed by the target application. So in this scenario, is we look at data from generated by the smart cards, and we look at our needs. We want to study the individual mobility. We found there is a gap because in the application of smart card transaction, basically they want to build this. They want to log this data for the payment purpose. So they have the data has a lot of missing value, and the frequency is also low. So there are a lot of data missing and uncertainty there. So we want to bridge this gap and try to find those missing data and use that for better recover the individual mobility. So later I will introduce what is missing in this data set. So these are the smart cards in different countries. I think in Taiwan, I also bought some smart card here. So in London, they have Oyster card. In San Francisco, they have Clipper card. Beijing, we call it Beijing BMAC card. Basically, it's I think it's just, all the cards are similar. So basically, you use this card for public transit. Also, you can use this card for in some small convenience store. To collect the user ground truth, we also have designed our own smart card in Beijing. We distribute this to our volunteers, and they report data to us. So this is a typical data set from the smart cards. So basically, in this data set, we have a card ID. This card ID basically stands for to identify which card it is, and it's usually one person has one card. So I think this usually can identify the person. And also this is the bus line number, so which bus line you take. And this is boarding and alighting stations. Boarding station means you get on the bus from this station. Alighting station means you get off the bus from this station. And this is the time for swiping your card. And this is the expense you just used, and this is the balance. So basically, this is a typical table for the data set. But you can find there are a lot of data missing. Why is missing? For example, for some buses in Beijing, if the buses is a fixed rate, we call it non-letter fare, then the data set will not include their boarding and alighting stations because they think this is not important, not necessary. And if it is not fixed rate, that means the fee is depending on the distance. Then we call it letter fare buses, and they will record the boarding and alighting stations. And this brings some challenges to the mobility pattern study because if we don't know the location where the user get on and get out of the bus, we cannot recover the mobility of users. So the problem is how we can recover these values. We try to leverage some other data sets. These data sets include data set from road networks. In Beijing, we have a data set for the Beijing road network, include a lot of road segments and the road cross. And also we have the user charging records. Charging records include how much they charge the card, deposit in the card, and what's the balance. And also we have the information about the Beijing bus lines. We, as I mentioned, we have designed our own smart cards, and we invite 100 users to use this smart card and try to report their data back. But this is only for the ground truth for the testing. We still have, we actually have also created a bigger data set from the bus websites. We have created data set from it's about 700,000 cardholders and about 20 million records during August 2012 to May 2013. So for this data set, is for training. So basically, if we look at this problem again, is we try to recover the missing value in this data set and know where the user get on the bus and where the user get off the bus for all the bus lines. So if we have this, and then we can easily find the user mobility pattern in this city. So this just illustrates our research is we have the user charging records, and we have the temporal timeline for the users. Here the user get on and get off the bus, and we want to get the exact geospatial location where the user get on and get off the bus. So we can have this trajectory data set of users. Yeah, so we try to link this and build a trajectory data set for the users. How we can do this? As the next, I will introduce our approach. So first, we want to segment user trajectories into different continuous paths. Here, continuous path means we know the user is continuously moving in this data set. To do this, basically, I think people may ask why we want to segment this, because the smart card record seems to be continuous at the beginning. But because there are data missing, or there are sometimes the crawler has some problem, so the data actually is not continuous. If it's not continuous, there may bring some noise to the algorithm. So first, we try to segment the data set into a continuous trajectory, and then we only work on one trajectory at one time. This segmentation, basically, we look at we call it monetary space. We don't just look at whether there is a big change in the balance. And we will define two types of transitions. Two types of transition means we call it inner transition and outer transition. That just means whether the user is transit on the bus or off the bus. For inner transition, that means the user is moving on the bus. For outer transition, that means the user is moving off the bus. We define these two types of transitions, and later we have defined three constraints. The first constraint is we call it proximity constraint. That means if the user is moving off the bus, that we assume that the user cannot move too far between two bus stations. For example, here is one bus line, the other bus line, and we found that the user have transferred from this bus line to this bus line. And we assume the transfer location will not be too far away. For example, the distance between A and B should be small. Here, the assumption basically is we assume the user will not walk too far to find another bus station. I think usually the user just find the nearest bus station and then the best transit location. And the second constraint is we call it fare constraint. That means because we still know how much the user pay on the bus, so we know roughly how long the user traveled on this bus for those non-fixed rate buses. For example, if we know the user paid like 1 or 2 yuan, and then we can assume this distance actually has a range. And the third one is called temporal constraint, because we know when the user swiped their smart card, and we know the typical bus speed. It cannot be too far inside the city. So we can estimate how far the user have traveled between these time points. So these are 3 constraints. And next, we define an algorithm. We basically we define the algorithm start from CRF. It's a conditional random field. We use this to try to label the user location sequence with the actual locations. So the sequence, basically for each node in this sequence, we have the observation of which bus line the user takes. We always know these bus lines. And for each node, we define the 2 consecutive bus lines as one node. And then we want to infer the actual location of this bus line, the user get on the bus or get off the bus. And then we have 3 constraints we defined from previous slides. This is not an algorithm proposed by us, this is existing algorithm. And we use these constraints to help this to add this constraint to the CRF and then optimize the final predictions. And we compare this approach with some baselines. The comparison we have carried out is with, for example, if we only base on CRF without these constraints, we can also get some result. And also we can use some heuristic to define some very simple approach. For example, we can always assume the user start from the last location, he just get off the bus, or from some popular location at this time point in a day. For example, we can assume the user always start from the same location in the morning and get back to the same location in the afternoon. So we have some heuristic for as baselines. And then we found that without constraints, the CRF actually doesn't perform well. It's similar to one of the baselines with heuristics. And with constraints, actually, the performance has been greatly improved. And next, I will introduce how we leverage this result. Because we have recovered the user location for get on and get off the bus, so we can better estimate the user mobility pattern. One of the tasks is to estimate the user home and the working place. If we because we have 100 participants, so these participants all reported their home and working place. And we found that before doing this data recovery, we can get some home and working place. And after this, the result have been improved by 88% on home and 35% on work. So the algorithm for home and work detection here is simple. Just we look at where the user is in midnight and where the user is in the daytime, like at noon. So we use this to estimate home and workplace locations. This home and work location detection basically I think is an important feature for personal assistant. As I mentioned previously, actually, a lot of companies like Google Now or our Cortana, they can all know your home and work locations if you have used this personal assistant for a few days. And I think this may have some privacy concern, so you can turn off. But if you turn on, it will try to remind you you need to leave your home early because of the traffic or because of the weather. So sometimes it's still useful. So this is sometimes it is very useful for users to catch their schedule. So to summarize, this work we have defined a space alignment framework. And we have defined approach for recovery missing data from smart cards. And based on this recovery, we found that we can get better home and work location detection result. And I think we expect this approach is not only limited to the smart card dataset. It can be extended to more similar datasets because this gap between the data generated by the service and data needed by the target application, it always exists. So next I will introduce another work on location recommendation. So for location recommendation, which is very important, for many personal assistant, it will recommend some restaurants or recommend some activities you can do for dinner or for the night activities. So in this work is our work in KDD last year. Basically, we want to use location history data to define better recommendations. So we look at location recommendation. I think people may be interested in what's the difference between location recommendation and general recommendation. For location recommendation, the problem is similarly defined. We want to understand the user potential interest, and we want to know the location, the surroundings of users, and then we want to discover the interesting values for users and recommend this value to users. But to better recommend locations, we want to leverage the geographical aspects of this data set. What are the geographic aspects? I think one phenomenon we found is users always move around some specific areas because users, for example, users have their home and the workplace or have some important locations. Users' activities always focus on these regions. So user is not moving randomly. Users have some activity centers. So to leverage this phenomenon, we define our algorithm based on this implicit feedback. For implicit feedback, which basically is a type of approach for solving recommendation. What is implicit feedback? Basically, in this implicit feedback problem is the users have not give explicit rating to the locations. Because there are different types of data sets. For some data sets, the user give ratings to movies and the books. So we know whether the user like this book or like this movie or not. But for location history, the user didn't give this rating. We only know the user have been to this location, but we don't know whether the user like this location or not. So the problem is we cannot directly use the frequency to indicate the user interest. That means if we see the user have been to one location for many times, that may not because the user like this restaurant. Maybe only because this is the restaurant, the only restaurant in the university. Because it's very close. So here, in the implicit feedback view, usually researchers assume that visit location only will imply the individual preference, but the frequency will not imply the level of the preference. They only imply the confidence of this preference. And for those visit location, because these location they don't have any negative sample. That means we don't know which location the user don't like because we only have location. The user didn't give any rating or negative feedback. For those visit location, that doesn't mean the user don't like this location. The user just may have not been to that location yet. So for those visit location, this location may be negative or positive, so we don't know. So this is the implicit feedback. And in this paper, in this work, we try to improve this implicit feedback by trying to better distinguish these unvisited locations. How to distinguish these unvisited locations? We look at the user mobility pattern. For example, if we know the user is working in, this is a map of Beijing. If we know the user is working here and the user's home is also maybe nearby, and for a location which is close to this region, we can assume this location the user may not like. But for a location is far away from the user activity areas, we can assume this location very probably the user haven't been to that location. So this may be just neutral. We don't know negative or positive yet. So here we try to look at the human mobility pattern and we try to define the user activity regions. And if some location which is far away from the user activity region, and we try to give a neutral rating for this location. But if a location is very close to the user activity reading. For example, there is a restaurant in the university, but you haven't been to that restaurant in the history. And then we can assume this, very probably this location, the user don't like this. Okay, so this shows the typical metrics. This is the users, this is the locations, and this just shows frequencies. And for those locations with this zero frequency, that means you have not visited this location, and we try to distinguish this location by looking at the user activity regions. Okay, so this is the model we developed. Traditionally, I think basically we look at this matrix. This matrix is the matrix here. So this matrix, we usually, researcher will factorize this matrix into two vectors. One is called latent vector for locations, and the other is, this is called user latent vector, and the other is called location latent vector. And based on our assumption is we try to add two vectors to this matrix factorization. One vector is we attach that to the user latent vector is, we call it user activity regions. So whether the user have activities in this region. And the other is we call it location influence area. We try to distinguish the different influence area for different locations or different restaurants. For example, some restaurant is very famous. People may travel far away to this restaurant. Or some restaurant is not that famous. Only local people will go to this restaurant. So we define these two vectors to incorporate the observations we found in previous slides. And then to optimize this factorization, we further define the objective function. So here, because we are using implicit feedback, so here the frequency here is a weight for the observations, and for the optimization for the object function, basically this is the traditional object function, and we add the P and Q, and we try to also minimize X and Y here. So in this paper, actually, we assume Y is given, and we only optimize X. And in the future, we will continue to study how to optimize X and Y at the same time. Here, X is the user activity vector. So here, actually, we define R. Here is the traditional, the original rating matrix, the frequency matrix, and the P and Q are traditional vector. And X and Y are the new vector defined by us. So here we, and the weight is the frequency. And as I've said, here Y is given because of the complexity. So here we only assume Y is given and optimize X. So for Y, here we just use a Gaussian distribution to define Y. So for a restaurant or some other locations, we define these grids, and on different grids in this region, we use set different values for the inference. And this optimization, basic optimization, is an iterative process. We first fix X and update P and Q, and then later we fix P and Q and update X. So we look at this optimization. We found that if we fix X, actually we are approximate R minus X multiplied by Y. So this, if we look at this, for a given user, if the user have not been to some location, so this actually depends on the frequency on this activity area of user U. That means if the user have been to this location a lot, then this very probably this will be a negative value. So for those visit locations around those frequent visit areas are highly likely to be negative. So this actually shows how we incorporate the observations into this optimization. Okay, so for experiments, we use we use the live spec data. We use the check-in data from Japan. Check-in is a social check-in website. Japan is a check-in website similar to Foursquare. We use 70% for training and 30% for testing. We compare different baselines here. We compare with the traditional user-based CF, and we compare with the Bayesian metric factorization, and also regular SVD such as traditional work. And also we use weighted MF, which is work for implicit feedback. These 5 are baselines. And also we study whether there is a spatial clustering phenomenon. Spatial clustering phenomenon means the user always move around some activity regions. These actually have been studied in the past. Previously used 2D kernel density estimation to estimate this phenomenon. So we compare with baselines. We found that if we add these 2 vectors to the implicit feedback, to the weighted MF, we call it GeoMF. It outperforms the result for the traditional weighted MF and GeoWSS. GeoWSS means we only look at those clustering phenomena. We don't use the traditional user and the location vectors. Okay, to summarize this work, this is for location recommendation. So here we use a 2D kernel density estimation for geographical modeling, and we use this to revise the traditional weighted metric factorization and adding 2 new vectors to reflect our observation. And we propose this GeoMF model for joint geographic model and the metric factorization. And we found that we also proposed a linear algorithm for optimize this, and we found the result is better than those previous baselines. Okay, to summarize my talk today, basically we started with human behavioral data. So we have seen a lot of human behavioral data have been accumulated, including their location data, including their data on sensor data on the phone, including those data review or social network data on the websites. And we are interested in first in understand the human mobility and how to recover the mobility from this data set, and how to use the mobility data for better location recommendation. We are also interested in profiling the users and also a group of users. And we are also interested how to protect the privacy of this user data. So in the future, there are a lot of challenges. First is privacy. I think if we mine this user knowledge, user may always have some questions about how we mine this data and how we use this data. So we need to explain how we protect the privacy of the user. And second is how we can get data from multiple sources. I think it's always difficult to get data. I think this data sharing problem is also a challenge for us. I think in the previous session, people mentioned interdiscipline. I think this is also our interest. How we can invite people from other domains, like from sociology, from psychology, to work together on this user understanding, user modeling problems. And how we can better manage large-scale heterogeneous data, I think is always our challenge, because these data basically are different kind of data sources and different types and different formats. So how we can better manage this heterogeneous data and work together, I think is a challenge for us. So thank you. I think that's all for my talk today.
Okay, thanks, Dr. Shes gives wonderful talks today. I think the user's location information is getting more important in this recently. So it may be worth starting it. There are more applications on such issues. So any questions? I think we have time to allow a couple of questions. Yes. Yes.
Thank you very much for that. Can you explain how this, where people are, is going to be used, what its application is going to be?
Yeah, so there are a lot of applications for using this user knowledge. As in one application we mentioned here is location recommendation. So we can, if we have this user data, we can better understand user interest. So we can recommend like good restaurants or activity or books or movies to the users. And also we mentioned the personal assistant and chatbots. If we have this understanding of user, the personal assistant or chatbots can have a better conversation with the user. For example, as I have given some examples. If the personal assistant knows you always sleep too late, they can give some advices to you to care about your health. So these are some challenge, some applications.
So how you differentiate between different trips? For example, I may travel on business or personal. My spendings would be different, my behavior will be different based on whether it is personal or family or business or something else.
Yeah, this is a very interesting question. I think purpose we have work on along this direction is we try to categorize the user trajectory in different purpose. Definitely, I think this is not easy. I mean, if we only look at trajectory, even human cannot distinguish the purpose is for business or sightseeing. But I think this is interesting. Purpose I think it's in 2008 we have a work on W. We try to use the photos, trajectories in the photos to categorize the user hit location into different purpose. And I think it's also useful for the data inference, because previously we have defined how we can distinguish local people and non-local people. But here, if we know that it's a business trip or it's a sightseeing trip, it's definitely useful for location recommendation. Yeah, so definitely I think this is very good research problem, and we have tried to solve from some perspectives, but I think it's not finally solved.
Okay. Is anyone? And I think we have a lot more questions because we have still about 4 or 5 minutes, right? Yes. Is anyone? So, okay. Yes, Rena.
So you mentioned about your phone catching your behavior, right? So if I turn off my phone because I got on the flight, it's different than I turning off my phone before I go to sleep, right? So how you can do you use the coordinates of my location, or you keep my home, my office?
So you care about privacy, so you try to prevent us from logging our location. You can always turn off this function before you turn off the phone, actually.
Yeah, of course.
Yeah. So I think for the flight, I think for many personal assistants like Google Now and Cortana, we read your short message and email to get your flight information. So even you turn off, we still know your flight schedule. So that's different. Yeah.
Yes. So, is anyone want to follow, or is there another new question? So, okay, there's no questions. So we very appreciate Professor Dr. Shear's appeal to give us the courageous speech here, and I think it's a very wonderful concluding of our conference, and let's give a big applause to Professor Shear. Okay, thank you. Thank you very much. And we have the president for Dr. Shear, and
ladies and gentlemen, thank you for all your stay to the next minute. And I have 2 announcements. First, about the lunch. Today we will have the lunch just next this room on my left-hand side. Okay. And about the city tour, if you want to join the city tour, please go to the